So the next force we're going to talk about is Coriolis Force. And Coriolis Force is an apparent force. It's a result of motion in a non-inertial coordinate system. So what does that mean? What's an inertial reference system? An inertial reference system is one fixed to the stars. And you know that our Earth rotates so that we see different stars. We see the stars actually move in the sky. So we are in a non-inertial reference frame. If you're in a spaceship traveling through space, you're looking at reference to the stars which are not moving, and that would be an inertial reference frame. So the Earth is non-inertial reference frame, and our X and Y and Z coordinates are rotating with the Earth. And as a result of that, it gives us an apparent motion to anything that is moving through our atmosphere. So we're going to start out with something that you probably know already, and that's the angular rotation or angular velocity of the Earth, which is 360 degrees in 24 hours or 15 degrees in 1 hour, or 2 pi radians in 24 hours. If you further divide that out, you'll end up with and convert that to 7.29 times 10 to the minus 5th radians per second. We've talked about this already. So the Earth is rotating at that rate. That's what we're going to call omega, big omega. Now, if we have something that's traveling through space at a certain velocity, it's with reference, we can reference it to an inertial reference frame. It's moving along unaccelerated. But let's put it on a non-rotating Earth. If that's the case, then it looks the same. If the Earth is not rotating, not spinning, then it moves through space, and in this case we're just having it move from the North Pole to the equator. And if it's moving at that velocity, it takes a certain amount of time to go from the North Pole to the equator. Of course, velocity is equal to distance divided by time. So that distance from the North Pole to the equator is simply the velocity times the time. Now, let's set the Earth in motion. We're going to spin the Earth and see how that affects our apparent motion. So there's the rotation. And as the Earth rotates, the object that's moving through space or through over our Earth's surface is moving at a velocity of v, and the time that it takes to go from the North Pole to the equator, the Earth actually rotates a certain number of degrees, and we can calculate that movement, that angular movement, because we know that the angular rotation rate of the Earth is omega. Multiply that by time, and that gives us the number of degrees or number of radians that the Earth has moved in the time that it takes for the object to go from the North Pole to the equator. So in other words, it's moved a certain distance. The Earth has moved a certain distance. It's moved a certain distance s. And we're going to call that our arc length. So as it travels from the North Pole to the equator, the Earth rotates, and it rotates through a certain number of degrees. And if you measure that distance, that is our arc length. And we have an equation for arc length, and that's simply the angle in radians times the radius. So we're going to say radius is r, and we're going to say the angle is alpha. So we already came up with some expressions for alpha and for r. We know that the time that it takes for the Earth to rotate a certain number of degrees, that distance or that angle is actually omega times t. It's the number of degrees per second times the number of seconds. So that'll give us angles. It'll give us degrees. It'll give us radians. So that's what the omega t is. And then we know that your r, the distance from the North Pole to the equator, is the velocity that the object is traveling over the Earth times time. So if we stick that into the equation, for r we'll use vt, for alpha we'll use omega t, and when we multiply those together, our arc length is now the velocity times the angular rotation of the Earth times the time squared. We also know from physics that a distance or displacement is equal to 1/2 times the acceleration times time squared. This looks an awful lot like the equation we just came up with. We have 1/2 at squared, and we have v omega t squared. Since those are both displacements, we're going to set those equal to each other and then start canceling things out. So the t squared disappears, and the 2 will move on to the other side, and we'll solve for acceleration. So acceleration is 2 times the velocity of the object moving times the angular rotation rate of the Earth. 2 times v times omega is your acceleration. Now, what we really want to come up with, what we're looking at, is forces. We've talked about the force it's resulting from pressure gradient. We talked about gravitational force. So Coriolis force, and we define forces as masses times acceleration, mass times acceleration. So we've got an acceleration, it's 2v omega. Multiply that acceleration times mass, and that gives us a new expression that we can use for the Coriolis force, which is 2 times mass times the velocity times the angular rotation of the Earth, omega. That is our expression for Coriolis force. Now, we know that Coriolis parameter, we talked about Coriolis parameter and the Earth's vorticity, how it varies from the equator to the North Pole. And the same is true for Coriolis force. It varies, because the Coriolis force, you can think of it as proportional to the angular rotation of the vertical. And we did this in class, if you remember, when we brought in the Earth, and we actually looked at how the local vertical rotates. And that's a measure of the Coriolis force. So Coriolis force varies with latitude. It's greatest at the North Pole, and it's weakest at the equator. So, with that in mind, we can come up with an expression for the variation in Coriolis force with latitude. And to do that, we have to visualize exactly what is Coriolis force. And Coriolis force is a vector that's actually pointing perpendicular from the Earth's axis outward. So that's what that arrow 2mv omega that we're looking at right there. And you can break that down into components. We can look at a component that's in the vertical, and we can also look at a component in the XY plane. So to do that, we have to use a little bit of trigonometry, and our component on an XY plane, in other words, on a weather map, would be the sine of that latitude times omega. So it's the sine. So there's Coriolis force that acts on just about any object that's moving. And that's where that V comes from. If something is moving, then Coriolis force is acting on it. And of course, the faster it's moving, the bigger the V, the bigger the Coriolis force. So this is our expression for Coriolis force. And you remember from a previous lab and also previous discussions that 2 omega sine phi we call the Coriolis parameter. So we'll substitute the letter F for 2 omega sine phi into this new equation, and it becomes a little bit shorter. And what it says is the Coriolis force is the mass times the Coriolis parameter times the velocity. Now, I want to stress that the velocity of an object traveling through the Earth's atmosphere is directly proportional to the Coriolis force. So, in the northern hemisphere, when an object is traveling through the Earth's atmosphere, it appears that it is deflected to the right as a result of Coriolis force. And in the southern hemisphere, an object that's traveling through the Earth's atmosphere appears as if it's deflected to the left because of the Earth's rotation.